Hey guys, in this video we're going to talk about mechanical advantage and some simple machines. We're going to go ahead and jump right in. So if you're like me, you've seen something like some guy using a rope with a pulley and lifting some gigantic piano and wondered to yourself, how is he doing that? I know he's not that strong. Or maybe you've tried to turn a screw with your finger and you couldn't do it. You probably cut yourself. It was really painful. But then if you use a screwdriver, it's a lot easier. Or maybe you're trying to pry open a can or pry something up, but you can't use your fingers and you can't lift it. But if you stick a ruler or a screwdriver or something under it, it makes it a lot easier. You might wonder, how does this work? Well, the answer is mechanical advantage. So basically, your simple definition is mechanical advantage is the ratio of output force to input force. In other words, you want to be able to put in a small force and get out a big force to move something. Now, this works by manipulating distance, which we'll look at in a minute. A lot of times, to be able to put in a small force, you have to move that force a long distance. If you've ever seen somebody turning a crank and you have to spin the crank around 100 times or something to move an object a foot, well, that probably means you're getting a lot of mechanical advantage. So, there are two types of mechanical advantage. There's ideal and there's actual. So, let's start with ideal. The ideal mechanical advantage is, theoretically, based on the setup that you've got, how much advantage should you get? Actual means in the real world, in actuality, in reality, when you take into account things like friction or parts that don't work that well, how much advantage are you actually going to get? And we're going to look at a really, really simple example here, the seesaw. So, if you're like me, at some point when you were a kid, or maybe an adult, you sat on a seesaw. And I want to tell my weight here. Let's say I sit on the right side of the seesaw, weigh about 170 pounds, give or take, 20. And my friend, or maybe my brother, if we're being realistic here, sits on the other side. And again, your goal when you sit on a seesaw, or at least my goal, was to vault my brother up in the air. I wanted to make him fly through the air. Well, as it turned out, we were right about the same size. So, if we both sat on the end of the seesaw, the same distance from the middle, and we both have the same weight, what do you think is going to happen? Well, the answer is nobody's going to move. Nobody's going to move there. Because we are both, 3 feet from the middle, and we both have the same weight, or the same mass. So, if we're looking at ideal mechanical advantage, your actual equation here for IMA is the distance of your effort force. So that would be this right here, divided by the distance of your resistance force. And I know I'm using some terminology that I haven't described yet, but we will get there. So, that is the ideal mechanical advantage here. It's based on distance, purely about how far you are away from the fulcrum. Now, in reality, we have what's called AMA. And it's all about how big of a resistance force can you move with your effort force. So the definitions are a little bit self-explanatory here. You have the effort force, which I'll say that's me over here. My effort force is me sitting on the seesaw. So my effort force is going to be 170 pounds here. The resistance force, that's the force or the load that you're trying to move here. So in this case, the resistance force is going to be my brother, sitting on the other side of the seesaw, just smugly looking at me over there. So, in this case, they're the same. So if we look at the actual mechanical advantage, we would do 170 pounds divided by 170 pounds, and my mechanical advantage is just going to be 1. Okay? A mechanical advantage of 1 means your output force and your input force is the same. In other words, you're getting out what you put back in. So if we look at the ideal mechanical advantage, in the real world, we use the effort distance. What that means is how far is my effort force away from the fulcrum, in this case, divided by the resistance distance. Same thing on this side. How far is my brother's force away from the fulcrum? So it's going to be 3 feet, or however long a seesaw is, I don't know, divided by 3 feet. And again, you get 1. So in this case, they're the same. Although in reality, that probably would not happen very often. So let's use a similar but slightly different example here. Let's rewind a little bit. Back to when I was in school, I was pretty small. I was probably a little closer to 100 pounds in high school. Let's say I was on the seesaw with a bigger kid, and I realize if he sits on the outside and I sit on the outside, I'm going flying through the air. I lose the game. Not much I can do. But I've got science on my side. So I tell the bigger kid, hey, why don't you sit in the middle? It's cooler that way. So he does. Say he weighs about 170 pounds. And it works out for me. We end up being balanced. It's perfect. So the way this works is I'm actually getting a mechanical advantage. So we're going to calculate ideal and actual mechanical advantage here. So first, ideal. So I'm still 3 feet away. I'm sitting on the edge. Since he sat in the middle, he's about 1.5 feet away. So for ideal mechanical advantage, or IMA, it's going to be the effort distance. How far is my effort force away from the rotation axis, divided by the resistance distance. In other words, how far is the resistance force away from the axis. Pretty straightforward here. 3 feet divided by 1.5 feet. And since the units cancel, mechanical advantage is not going to have a unit here. It's dimensionless. So ideally, my mechanical advantage should be 2. I have a 2-to-1 advantage here, meaning I can move a force that's twice as big as me, since I am twice as far from the middle. I get a 2-to-1 advantage. But if we look at the numbers, he's not quite twice as big as me. He's bigger than me, but not quite twice as much. So what that means is the actual mechanical advantage is not going to be that big. Let's calculate it to be sure. So again, with mechanical advantage, you typically want a big resistance force for a small effort force. So we're getting 170 pounds divided by my muscular 100-pound frame. Units cancel, and it looks like the mechanical advantage that I'm actually getting is 1.7. Now there's lots of reasons for this. I think I mentioned friction at the beginning of the video. That's typically what it is. And what that might be in this situation is, I don't know, the seesaw is pretty rusty. I'd be afraid I'd get tetanus on the seesaw that we had when I was on the playground. So that means it doesn't necessarily rotate perfectly. So it might stick a little bit, and I'd have to push a little bit harder. So I'm not getting quite the advantage that I would ideally. So we're going to move on and talk about some other types of simple machines real quick. So there are actually 6 types of different simple machines that you can use to manipulate force and distance here. So the first type is the lever, like we just talked about. The second type would be the pulley, which I mentioned at the beginning. Next would be the wheel and axle. Next is the incline plane. You've got the screw, and you've got a wedge. So you see most of these, if not all of these, every day at some point. And again, like I said, you're always manipulating force versus distance. If you've got some crazy pulley system set up, which we'll talk about in a later video, where you're lifting some huge force, let's say this is a piano or something, and here's some little dude holding it. Oh, that's a terrible picture. So he's happy. He's not even struggling because he's got such a good mechanical advantage. So, again though, for him to lift, if he's getting a big mechanical advantage, for him to lift it this far, he might have to pull the rope this far. Because he's getting more force output, he's having to input more distance. So he'll have to pull the rope further. Whenever we do the pulley video later, you'll see some specific examples of that. So thanks for watching the video. I hope you learned something. I hope you enjoyed it. If you want to learn more, there's going to be individual videos about each of the 6 types of simple machines. So please check back in with those for practice problems, more beautiful artwork, or strange childhood stories about me seesawing my brother through the air. I guess that's it. See you next time.